Welcome students. In this lecture we are going to discuss examples related to two samples t-test of means. This is in continuation to the examples we had been discussing related to the t-test of means. Remember, the t-test of means is a hypothesis test, and we have discussed the theory related to the t-test of means regarding both the one sample t-test of means and two samples t-test of means. And in this lecture we are only discussing the examples related to the theory that we discussed. Just to remind you, in two sample t-test of means, we have two samples taken from the two populations, and with the help of these two samples, we do the hypothesis test about the difference of means related to the two populations. So, example number one. The example number one is that in a packaging plant, a machine packs cartons with jars. It is supposed that a new machine will pack faster on the average than the machine currently used. An experiment was conducted to record the time taken to pack 10 cartons by new and the old machine, which is also the present machine. The results in seconds are shown in the following table. Now, using 99% confidence interval, test the claim that new machine will pack faster than the old machine. We have done this example previously in the estimation of the differences of mean. Now we will use the same example but for a different idea, which is the hypothesis test. So we have two samples. Sample one belongs to new machine and sample two belongs to old machine. And we have the statistics for these samples as well, like the sample size, the mean value and the standard deviations. And we basically assume this thing rather that sample one, which is belonging to the new machine, can be written with a population mean of mu1, not the sample one, rather its population can be written as with the population mean mu1, and sample 2, which belongs to the old machine, is assumed to be taken from the population written by the population mean mu2. So what's the procedure of the test? We first write the hypotheses that are present over here, but before doing that, we must realize that this is an independent means two sample t-test because the samples are taken from two separate populations. So we write our hypothesis. The null hypothesis would be the standard null hypothesis for a two sample t-test of mean. Please note this thing that the null hypotheses are standard statements. We cannot change them. So for the two sample t-test of means, the null hypothesis is mu1 is equal to mu2. There's no difference between the two populations, or this can also be put it in this way that mu1 minus mu2 is basically equal to 0. Then the alternate hypothesis. Now, what should be the alternate hypothesis? The statement of the alternate hypothesis would come up from the question. What is the question? The question is that we have to test the claim that new machine will pack faster than the old machine. Since these are all the time values given to us in the samples, and we know that lesser the time, the faster its operation is. Therefore, the alternate hypothesis is mu1 is less than mu2, where mu1 is the population mean for the population 1, which is the population of new machines, and mu2 is the population mean for the population 2, which is the population for the old machines. So the alternate hypothesis statement is mu1 minus mu2 is less than 0, or mu1 is less than mu2. Because when mu1 would be less than mu2, then definitely their difference, if in where mu1 is coming first, then their difference would also be less than 0. So this suggests that it is a lower tail, one-tailed t-test of mean, or one-tailed test of means. So in the next step, we find the sample statistics. We have the sample size, which is 10 for sample 1, and for the sample 2, it is again 10. Then the sample mean is given to us. The sample mean for sample 1, that is sample 1 sample mean is x1 bar, which is 42.14, and sample 2 sample mean, which is x2 bar, is 43.23. Next, we find the standard error of mean, which is the ratio of the standard deviation of the sample given by given in the question, and so it's a ratio between the standard deviation of the sample to the square root of the sample size. So we have S1 as 0.683, and when it is divided by the square root of 10, we get 0.2159. If we take the variance of this, then we get S1 square upon N1, and this is 0.0466. The SEM For the second sample is basically S2 upon under root N2, which is 0.750 divided by under root 10, and the answer comes out to be 0.2371. And if you want to find the variance of it, then it is basically S2 square upon N2. So that should be S2 square upon N2. Let me just rectify this little typo over here. So that should be basically S2, just S2 square upon N2. And we get the answer, which is 0.0562. Whereas 2 is the standard deviation of the sample 2. Next step is about finding the t statistics. And for the t statistics, the equation that we are using is the same one that we used earlier as well. So this equation, which is basically Ts equals to x1 bar minus x2 bar minus mu1 minus mu2 upon under root s1 square upon n1 plus s2 square upon n2. Remember, this is the same equation that we used in the estimation of the differences of mean. Please note this thing. This is very important to understand, that this equation is the product, or it is the output, when the central limit theorem is assumed to be true. When we have central limit theorem, we mean by this that the samples that are given to us are taken from the sampling distributions, and more particularly, the sample means that are given to us, they've been taken from the sampling distributions of means of the two separate populations. And by CLT, or central limit theorem, we know this thing, that the sampling distributions of means is normally distributed. And when it is normally distributed, we get these t scores, which is written over here as TS value. So because of CLT, we can write this t score or the t statistic in this way. Okay, so this is the same t statistic that we had in the estimation of the differences of mean as well. The next step is plugging in the values, but we should note this thing, and that before plugging in the values, we should note this thing, that mu1 minus mu2 in the null hypothesis statement is 0, and depending upon whether we have equal variance or unequal variance, we have t statistic given as follows. So since we have to first check that is it a case of equal or unequal variance, so we take the ratio of S1 upon S2, and we get 0.683 upon 0.754, which is basically 0.9106, and which satisfies the case of equal variance. And for the case of equal variance, we first have to find the pooled standard deviation, which is given by this formula. Again, this formula is the same one that we use for the estimation of the differences of means. So we plug in the values, the ingredients of this formula, and get SP, which is 0.7173. Now we are able to basically plug in the values of SP in the TS equation, the T statistic equation. And when we plug in all the values of x1 bar, x2 bar, SP, and n1 and n2, we get a result, or a t value, which is equals to minus 3.3988. So this is our t value in this case. Step number 4 is about finding the critical t value, and this is obtained from the t table using the degree of freedom and confidence interval that is provided to us. The degree of freedom in our case is n1 plus n2 minus 2. This is the degree of freedom that we use for equal variances, and this is 10 plus 10 minus 2, which is 18. And from the t table, we get a critical t value, which is minus 2.552. Now, how did we get this value? Let me show you. So we have the t table over here, as we can all see, right? Since this is a one-tailed test, therefore, on the row of one tail, and the column is 0.01, the level of significance was 0.01 in our question, and then the degree of freedom was 18. So where this row of 0.01 on one tail and row of 18, degree of freedom 18 intersects, this is our t value, which is 2.552, right? Now please note this thing, that only the positive values of t are given in this table, but it is true from the construction of this table that the same values in the negative can be written. Like for example, since we had our t as negative, Therefore, the corresponding critical T value should also be negative. And instead of writing 2.552, we have quoted the value of Tc as minus 2.552. Now, in the step number 5, we are comparing Ts with Tc, and we can see this thing that our Ts value, which was minus 3.3988, is far lesser than the critical T value, which is minus 2.552. And what does it mean? It means that uh, on a sampling distribution of mean of the H naught population, right? The the TS value is basically lying in the region of rejection. That is the region which does not belong to the H naught population. So since it does not belong to the H naught population, therefore it will be belonging to the other population, and the other population is the HA population. So since it is not part of the H naught population, therefore this sample does not belong to the population of null hypothesis, and surely we would be able to state this thing that we can reject the null hypothesis. By rejection of the null hypothesis, we mean that our sample does not belong to the H naught population, as we have discussed this thing in the previous examples as well. So depending on 5, if to decide to reject or not reject the null hypothesis in step number 6, and since TS is in the region of rejection, or it is in the rejection region, therefore we have enough statistical evidence to reject the null hypothesis. So this was example number 1 for two sample t-test. I hope this is understandable to everybody. If there are any queries, so you can write down in the comments, and then we can discuss it later on, or I will reply to your comments so that your queries can be resolved. Example number 2. Independent random samples of 17 sophomores and 13 juniors attending a large university yield the following data on grade point averages. By not assuming equal variances at 5% level of significance, do the data provide sufficient evidence to conclude that the mean GPAs of sophomores and juniors at the university differ? This is a good question, and we have already discussed this question when we were talking about, or when we were learning the estimation of the differences of means. Now we will be using the same data set, the same question, but for a different case, and this is for the two sample t-test of means. So let's see how this thing happens, how we perform the two sample t-test of means. So firstly, we should realize that this is again the case of independent means two sample t-test. The first step, we formulate our null hypothesis and alternate hypothesis statement. The null hypothesis is basically a standard null hypothesis statement in a two sample t-test, as it is for any other test. It is a standard statement, and initially we start our null hypothesis with assuming that there is no difference between the populations, that is mu1 is equals to mu2, or it can also be put it in this way, that mu1 minus mu2 is equal to 0. Now the statement of alternate hypothesis will come from the question. In the question it says that do they differ. By the word differ, it means that they can be greater than, one can be greater than the other, or one can be less than the other. So when we have this, when any of the cases are possible, we basically write it in this way, that mu1 is not equals to mu2. And this suggests that it is a two-tailed test of means. Step number 2, you have to find the sample statistics. So the sample statistics are the sample sizes, sample means, and the standard deviations and SEM. So for sample 1, we have sample size 17, and the sample mean is 2.84, and the SEM is S1 upon under root N1, which is 0.5056 upon root 17, which is 0.1226, and the variance is S1 square upon N1, which is 0.0150. For sample 2, we have the sample size equals to 13. The sample mean x2 bar is 2.98, and SEM is S2 upon root N2, which is 0.2971 upon 13 under root, and this gives 0.0824. And again, there's a typo. I can see the variance would be S2 square upon N2 rather than S1 square upon N1. So let me correct this thing, this typo over here. It should be S2 square upon N2 for the second sample. It should not be S1 square upon N1. So we got this typo again, but never mind. We'll correct it. So we have S2 square upon N2 So S2 square upon N2 is basically 0.00678. Step number three is finding the t statistics. We call them t statistics because these are the t values obtained from the sample parameters, and the sample parameters that would be used for the t statistics are written over here in the equation. This equation is the same as it was for the previous example, and we must realize again this thing that this t score can only be used when we assume that we are uh, satisfying the requirement of central limit theorem. That is, and we assume that we are satisfying. That is, our samples have been taken from the sampling distributions of means, which is normally distributed for both the populations, and therefore we can make use of the t-score as written over here. So again, it is to be noted that from the null hypothesis, mu1 minus mu2 is equal to 0, and we have the case of unequal variance. Um, Therefore, we have the t statistics given as follows, that ts equals to x1 bar minus x2 bar minus mu1 minus mu2 upon s1 square upon n1 plus s2 square upon n2 under root. So when we plug in the values, we get something like minus 0.9491. So this is our t value, or the t statistics value, or ts value, which is minus 0.9491. Everything that is required to find this value using this equation is given to us. So we just need to plug in the values of means and the standard deviations and the sample sizes, and we'll get the result. Step number 4 is finding the critical t value. This is obtained from the t table using the df and ci. The ci is 95% and df is calculated as follows. For the case of unequal variance, this formula was discussed in detail in our lecture of estimation of the differences of mean. And when we plug in the values for df, we get an answer which is 26.505, which is approximately equals to 26. So that critical t value that we obtain from the table, uh, which is shown over here, that in the df row of 26 and in the two tail of 0.05, we get 2.056. So 2.056 is our critical t value. Next, in the step number 5, we have to compare our TS with the TC. Our TS was minus 0.9491 and our TC is basically minus 2.056, and it shows that our TS is far much greater than the TC value. And again, please note this thing, that we have put the TC value as a negative value because our TS was negative. In our t table that we are using, only positive t values are given, but it is assumed the same can be used for the negative t values. So this shows that since our ts is greater than tc, this shows that our ts is lying not in the region of rejection but in the region which belongs to h naught. So therefore, our sample is taken from the population of H naught. Therefore, uh, definitely we won't be able to reject the null hypothesis. So in step number 6, on depending upon step 5, we decide to reject or not reject the null hypothesis. And since TS is not in the region of rejection, therefore we do not have enough statistical evidence to reject the null hypothesis or the H naught value. So this was for example number 2. I hope it is understandable to everybody. Let's move on to example 3. Trace metals in drinking water affect the flavor, and an unusually high concentration can pose a health hazard. 10 pairs of data were taken measuring zinc concentration in both in bottom water and the surface water. Thus, the data suggests that the true average concentration of the bottom water exceeds that of the surface water. The data obtained is as follows. Now, this is the same example, the same question that we discussed in our estimation of the differences of means. The story is this, that we have taken 10 pairs of samples or 10 pairs of data to create two samples from the same population, and one is the sample taken from the bottom surface of water, and this includes the zinc concentrations, and the other is the sample taken from the top surface of the water, and this is the zinc concentration over there. So we have this data set, and as we work in the estimation of the differences of means, we would be using the similar formula over here as well. So first, we should realize it is the case of dependent means or two samples t-test. It's the case of dependent means two sample t-test. Uh, Step number 1 is formulating the null and the alternate hypothesis statements. The null hypothesis is a standard. and this states that mu d is equals to 0. Please note this thing, that mu d is the population mean of the population, which is the differences of mean population. And this differences was it's basically the population mean of the population, which is the which is the differences population. Sorry, and this differences population was obtained by subtracting the two subpopulations which were created in the single one population, right? And we write in the hypothesis that mu t is equals to 0. That is, there's no difference between the two subpopulations. And since we have to find that uh, the water in the bottom surface, the true average concentration in the bottom water exceeds that of the surface water related to the zinc. Therefore, the mu t is greater than 0. In this case over here, mu t is greater than 0. By writing mu t greater than 0, we basically mean in this thing that mu1 minus mu2 is basically greater than 0. You can also put it in this way, where mu1 is the population of bottom surface of water containing and putting the zinc concentrations over there, and mu2 is the population of the zinc concentrations from the surface water. So it suggests that it is an upper tail test and one tail test of mean. Let me correct this typo over here. So it is basically a one tail test of mean. Step number two is finding the sample statistics. This includes the sample size, which is 10 over here, the sample mean, the XT bar value, and the SEM, the ST upon under root n from the new differences data set. And this is done as follows. So we have a table which includes sample 1 values, sample 2 values. They were taken in pairs. And the third column is the differences data set, which we call the XT uh, data set. And this basically includes x1 minus x2 values. The mean of this xt is found to be 0.0804, and the standard deviation of the new differences data set is found to be 0.0523. And the SEM, which is SD upon under root n, is found to be 0.0523 upon under root 10, which is 0.0165. So in step number 4, let's plug in these values to get the TS value. Again, this is the same one. This is the same T score that we have been using, assuming that the central limit theorem is satisfied, and we have been discussing a lot about it in our previous examples. So the same applies over here. So TS is calculated to be 4.8727. It's a big value, right? It's a big value. Please note this thing. It should be noted that from the hypothesis, mu d 0 has been used in this equation. Now, step number 5. Sorry, please, I just want to rectify another typo. This was not step number 4, rather, it was our step number 3. So, this was our step number 3, and now it's all okay. So, in step number 4, we find the critical T value using the DF and the CI. The CI was 95%. And the DF is n minus 1, that is 10 minus 1, 9. Okay, I want to notify you this thing over here, that many times in the questions the CIs are not given. When it is so, then you can assume that the standard CI is 95%. If it happens so, then you can assume that the standard CI is 95%. Like in this question, um, was the CI given? Okay, in this question, the CI was not given. So you can assume that we are working on 95% confidence interval. This is a standard way of working. So at 95% confidence interval and DF, which is 9, using the T table, we get a critical T value, which is 1.833, which can be seen from this figure as well, that on one tail row and DF and the 0.05 level of significance being used is the column, and TF is basically 9, so we get the T value, which is basically 1.833. Since our TS is positive, so T would also be taken as positive over here. In step number 5, we compare to see if our T statistic TS is greater than, less than, or not equals to TC. And basically, this means that on the diagram of the null hypothesis, which is shown by the sampling distributions of mean, where our TS value is lying. So we can see that since our TS is much greater than the critical T value, This basically means this thing that we are lying in the region of rejection. Very confidently, we are lying in the region of rejection. There is a region which does not belong to H naught, rather it belongs to the other hypothesis or the other population, which is HA. So in step 6, depending upon 5, we decide to reject or not reject the null hypothesis. And since the TS, T statistics value, is in the region of rejection, or it is in the rejection region, therefore we have enough statistical evidence to reject the null hypothesis or H naught. So that is it from my end. We have discussed three examples of the two sample t-test of means. Previously, we have discussed also examples related to the one sample t-test of means. So the hypothesis testing of the t-test of means is completed. If you have, again, I would repeat it, if there are any queries, any confusions which you want to discuss or you want to ask, then you can write down in the comment section and I'll get back to you to answer your queries. Thank you very much.